Hello scholars, welcome. Mr. Hinkle here. And to introduce the concept of geologic time, we are going to talk about how did we even get to this bright idea anyways through the concept of how old is the Earth? What is the age of the Earth? So the Earth has been around for a long time, about a third of the length of the solar system, roughly. And for as long as people were thinking about things, one of the big questions was, how old is the Earth? What is the age of the Earth? And it puzzled people for a very long time. They didn't have the means necessary to answer the questions, although through the ages, people attempted using what they had and what they knew. It's only within the last century or so, in the 50s, where we actually developed the tool set to actually decipher, to calculate the age of the Earth. But let's go back a little bit. 1650, the Archbishop James Ussher. Now, this is right before the beginning of the scientific revolution, and this individual was taking the Old Testament and he was interpreting what he was reading in the Bible to put an age for the beginning of the Earth based on creationism. And what he was able to deduce is that the Earth formed in 4004 BC before Christ, or about 6,000 years ago. And this held up within the Catholic Church, and it made sense according to the creationist model. But it didn't make sense when you're thinking about geological processes and how the things that are happening on Earth to shape it and form it the way that it is today occur over very long time scales. So let's fast forward right through the scientific revolution and get to Lord Kelvin. Yes, you may have heard of the Kelvin temperature system developed by this person right here. And he took information from Claudius Ptolemy almost, 2,000 years earlier, right? Claudius Ptolemy lived in AD 70, so 18, 19 centuries. He took this info on the circumference of the Earth, then he used that to try and calculate the age of the Earth. Now, he put the age at about 98 million years, but knew that his estimates were fairly inaccurate and said, oh, it could be as young as 20 million years or as old as 400 million years. And so we're talking millions of years now, as opposed to James Ussher, who came in and said 6,000 years. All during this time, we've got the Plutonists and the Neptunists. People don't even know how mountains are made. Did they happen catastrophic events underwater, Neptunists? Are they forged by fire through volcanoes? Plutonists, the Plutonists ended up winning out that debate. The world wasn't shaped from some great flood or at the bottom of the ocean, but it's through geologic processes over time. Anyways, let's keep going. Fast forward, 1950s. So early in the 20th century, a new technology came out for analyzing the isotopes. We could peek into the atomic level of rocks, of the different elements that make them up. And this process of radiometric age dating was developed. Through this, Claire Patterson was able to find certain rocks, meteorites, rocks that had arrived to Earth from outer space, and by looking at the relative proportions of parent to daughter isotopes, please see numerical age dating in another lecture, he was able to calculate the age of the Earth, 4.55, give or take 70 million years or so. 4.55 billion years old. Now, this is a fairly accurate number. 4.56 is the USGS accepted age for the age of the Earth. You could say it's approximately 4.5. I see it written a lot of ways, approximately 4.6. Now this is the Earth. Using the Big Bang theory for the expanding universe, we have calculated or back calculated that the age of the universe is approximately 13.77 billion or 13.8 billion years old. So here's the universe. Over here we've got the Earth. And let's just say that the universe and the Earth have been around for a very long time. And this is important because natural geologic processes like the formation and the creation of rock, the rock cycle, takes time. It needs time for these things to happen. So what does 4.55 billion years even mean? What does that even mean? Well, let's think about it. This is an image of a sheet of paper with 5,000 zeros on it. There's 10 zeros across and 10 zeros down. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There's 10 blocks in a row. 1, 2, 3, 4, 5. 5 rows. 5,000 zeros. Okay, so if we wanted to think about how many sheets of paper we would need to get to a million, we would need 200 sheets of paper. How many sheets of paper would we need to get to a billion? We would need 200,000 sheets of paper, each sheet of paper having 5,000 zeros on it. Let's keep going. If the age of the Earth is 4.55 or in this example, we're looking at 4.566 billion years old, that's 4,566, 000, 000. Well, you divide that by 5,000, and we get 913,200 sheets of paper, each with 5,000 zeros on it. Now, paper comes in bundles called reams, like so. There are 500 sheets of paper in this. If we take 913,260 divided by 500, we would need 1,826 reams of paper. So imagine this. Every sheet of paper in here has 5,000 zeros on it. Now you take this and stack it up 1,826 reams high, with each one of those pieces of paper having 5,000 zeros on it. Zeros representing years. How old is the Earth? It is a stack of 1,826 reams of paper, each ream 500 sheets, each sheet 5,000 zeros. That's a long, long time. So the whole purpose of this thought exercise is to start to grasp this idea of geologic time, deep time. The Earth has been around for a very long time. I think in terms of hours and days, months, years. Sometimes I reflect on decades. I don't think in centuries very often, unless I'm talking about history. But the Earth occurs on timescales of millions to hundreds of millions to billions of years. So geologic time is trying to reorient our minds into timescales that we do not think about on a regular basis. It is timescales that are much greater than we can comprehend. So when we're thinking about concepts and topics in geologic time, they occur over huge, vast time periods. So let's do a shout out of some of the oldest things that we know. The oldest mineral is a piece of zircon that survived through the rock cycle it's been dated to be about 4.404 billion years old in the Jack Hills of Western Australia. Now, this is a mineral crystal. It's not a rock that's in situ that can help us know what the Earth was like at that point, but it does give us an indication that in this metamorphic rock, there is a crystal that has survived. That's some of the oldest terrestrial rocks that we have. Northern Canada, we have the Acasta gneiss. Gneiss is a type of metamorphic rock. Metamorphic rock is any type of rock that has changed their form. And the minerals in this rock have been dated back anywhere from 4.0 to 4.4 billion years old. So, oldest specific mineral is going to be the zircon in the Jack Hills. Oldest rock features are going to be the Acasta gneiss in northern Canada. Oldest evidence of life comes to 3.5 billion years old. These are modern day stromatolites. They haven't changed much. They don't occur very many places, but the Sharks Bay in Australia is one of the few places on Earth where stromatolites believed to be the most ancient life forms, microbes that form mats as they grow on top of each other and grow through the sediment. They've been preserved in rocks. So this squiggly looking rock that doesn't look like much actually houses fossils. The most ancient fossils showing us the furthest back dated evidence of life. Now, life could have existed earlier, but as far as we know, stromatolites are it. We have evidence of stromatolites through fossils in the rock record. And Earth's oldest meteorite, the Diablo Canyon meteorite, which dates back to right here about 4.5 billion years old, this is believed to be the original ingredient, the original matter of the solar system at its time of formation. The sun is turning into a star as disks are accreting, and there's a lot of rocky and gassy material in the solar system. Now, most of this material condensed into planets, but some of it is just floating out there in the asteroid belt, floating out there in the Kuiper belt. So, asteroids are interpreted to be the same material that made the planets, it just didn't form into planets. Now on Earth, we have this constant recycling of Earth materials called plate tectonics. But when a chunk of rock arrives to the surface of the Earth from outer space, it arrives as a meteorite. And we use these meteorites to provide us the evidence for the formation of the solar system, saying that Earth is as old as this meteorite, and so is the solar system. So this is the age of the Earth to give us an introduction and an explanation of geologic time.